Just a little review then to see how you guys are sitting. Get a little peanut butter on your forehead there, Jeremy.
No, he not.
I'm not Jasper.
I was going there.
So looking at this transformer, what would the transformer ratio be? Do you remember? You've got the primary coil and the secondary coil. Is the ratio so that reduces to what? 5/8. There we go. You guys actually have a math person in here this semester to help you guys out. Yeah. We won't be seeing him for a while. So what that means is that the ratio of voltages is the same as the ratio of the turns in the coil. So this was the secondary, this is the primary. If on my primary side, I am coming in with 400 volts, what is my voltage on the secondary side? Yeah, 5/8. The 400 goes on the primary on bottom. To find that missing number, we cross multiply and divide. 5 times 800 divided by, or 5 times 400 divided by 8 is 250. This will be 250 volts. So the ratio of voltage is equal to the ratio of the turns of the coil. So let's have a high voltage transmission line, 10,000 volts. Does anybody know what the usable voltage is coming in basically for most lines that come up to your house or shop or whatever? Are you aware? $440. $440, $480, depending on how you rate it. Industrial, this is a 440 volt system. Like if 480, yeah. We'll rate it as 480. It's just like 110. Is it 110 or is it 120? How are they discussing it? You know? We'll put it down as 480 for you. But if there are, well, let's say there are 180 turns on the secondary coil here. How many turns need to be on this primary coil? Our transformer ratio is NS over NP, right? Which is going to be equal to our voltage ratio of VS over VP. Where's the 180 going to go? Left side top, right? That's my secondary turns and secondary coil. What goes on top over here? $480, good. That's the voltage in my secondary coil. On the bottom over there would be 10,000. That's my primary voltage. So now I need to find the turns here. I'm going to cross, multiply, and divide. I'm actually going to pull the calculator out for this one. 180 times 10,000 divided by 480, 3750. So you need 3,750 turns on that coil. That's called a step-down transistor, or step-down, transformer. It steps down the voltage to the usable voltage. Now it does go the other way as well. There are step-up transformers. Let's say you are running in a 24-volt system. You have primary turns of 40, and you have secondary turns of 110. Find for me in the notes the secondary voltage. What would that secondary voltage be? So we decide which one do we know both for, the turns or for the voltage? The turns. Doesn't matter which one goes on top. Say no. It really doesn't. I can put the 40 on top and the 110 on bottom. I just have to know that the 40 is the primary and the 110 is the secondary. The 24 then goes it's primary, right? Just as long as primary goes with primary and secondary goes with secondary, it doesn't matter which one goes on top. Cross, multiply, and divide. 110 times 24 divided by 40. 66 volts. Very good. Any questions on those? How about a bridge? We mentioned a bridge briefly last Thursday. A bridge looks something like this. So let's say, and what a bridge does is depending on the resistances in these four resistors, it can cause current to flow either direction across this center part of the bridge. It's a way of controlling it with a variable resistor. Of course, this is a variable resistor. It's a way of controlling the current flow and being able to make it go either direction. So the resistor, the bridge ratio, comes from the two resistors on the side that does not have the variable resistor. So that's just R1 over R2 is the bridge ratio. So let's put in some resistances. Let's say this is a 1.2 kilo ohm. And this down here is a, we'll go 3.2 kilo ohm resistor. So my bridge ratio, do I have to write it out as 1200 over 3200? No, I could, but since it's kilo, the kilo would cancel out, be 1.2 over 3.2. Now to reduce that I might make it 12 over 32. I just multiplied both by 10 to get rid of the decimal. And then divide out. Both of those can be divided by 4. So 3/8. 3 to 8. So that's a 3 to 8 bridge ratio. A balanced bridge is a bridge in which no current flows. For no current to flow, the ratio, R1 over R2, the bridge ratio, has to be equal to Rx over R. So for this bridge here, if Rx is 2.7 kiloohms, what do you have to set R2 to balance the bridge? Now, it doesn't matter if for R1 and R2, whether we go to the 3/8 or if we go back to 1.2 over 3.2. Really doesn't matter. The 2.7 goes in for Rx. Now we can cross multiply and divide. 3.2 times 2.7 divided by 1.2 is that 7.2? So we would have to be set at 7.2 kiloohms for that variable resistor to balance this bridge. Now again, why is that so important? Why is this bridge so important? For two things, it does allow us to run current in either direction. The second thing is because of that anywhere from 5 to 20% tolerance in those resistors, it allows us to measure the resistors and get exact ones and still be able to adjust to make it work. We don't have to have exact resistances in order to precisely control the current. So here, this one is going to be 2.8 kiloohms. 1.6 kiloohms. That's 4.2 kiloohms. What does our variable resistor have to be set at? In your notes, find that for me quick. Okay, tell me how you set her up.
2.8.
Okay. So then we'll cross multiply. 1.6 times 4.2 divided by 2.8 is 2.4 kiloohms. Any questions? Okay, let's say you currently have a system wired. You're wiring a system And currently you have used 48 feet of wire. You test the resistance in that wire, and the resistance of that wire is right now sitting at 8 ohms. You need it to be less than or equal to 6 ohms. What is the longest that wire can be? Well, in wire, the ratio of lengths and the ratio of resistances is going to be the same. So I have 8 ohms. I need to get it down to 6 ohms. Where's my 48 feet going to go? On the top, because that comes from the 8 ohm wire. So here, if I cross multiply and divide, 6 times 48 divided by 8 is 36. So I need to find some way to get that wire down to 36 feet. Run it a different route or whatever. Where this is most useful, let's say you have a spool of wire. I'm a little big and a small spool. Let's say it is a 300-foot spool. And it is listed that the whole spool has 24 ohms of resistance. How long of a wire can you run if you need to get less than or equal to 1.2 ohms? So again, our ratio of length and our ratio of resistances are going to be the same. Doesn't matter which one we put on which side. I usually put the one that I know both numbers for first. So let's put the resistances on the left side. What do I want to put in there for the ratio? 24 over 1.2 works for me. On the other side then is my wire length. Where's the 300 go, top or bottom? Top, because that is the full spool, which is what the 24 also represents. If we cross multiply and divide, we get, what, 15 feet? So we can go maximum of 15 feet. So same type of thing. We have a 480-foot spool. Spool that rates at, no idea. Let's say that it rates at 20 ohms total. You need 100 feet of wire. What resistance is that going to be? Okay, so we have the distances. Some put 480 feet over 100 feet. On the other side, where's the 20 go? Does the 20 go with the 100 or the 480? With the 480. So we cross multiply and divide. 100 times 20 divided by 480 is 4.2. Sounds about right to me. You're going to have a 4.2 ohms. Make sense? 4 1/6. That works too. If we did 4.17, I'd be okay with that, or 167. I didn't specify round offs. Okay, so next we want to talk about, I want to do a little bit of a review here on percent. Because percents come up. Do you need some time alone there to go fight this out, or percents? Now I'm not going to take a lot of time to talk about converting percents. I'm just going to put some examples up here and see if you remember how to do it. If I give you 48%, what is that converted to a fraction or a decimal? So to convert it to a fraction, 48% literally means 48 over 100. Now, of course, we can reduce that by what? What can we divide it by? Both can divide by 4, giving us 12 over 25 as a fraction. How about as a decimal? 0.48. Yes, it's just 48 over 100. If we divided that out, that moves the decimal point 2 spots. 0.48. Good. But what if I give you a decimal of 0.072? 7.2%. Okay. How about for fraction? 72,000. We can put it at 7.2 over 100, but we have to get rid of that decimal. And we do that, since it's one spot, we would multiply by 10. It would be 72 over 1,000. Now, of course, that can reduce by, both of those divide by 8. Give you 9 over 125. You guys have any questions with the converting fractions decimals? We're good? Okay. So in the basic calculations, blank is 40% of 90. Now, last semester we had discussed 2 different methods. One was the proportion method. In the proportion method, we always started with the percent. 40% became what? 40 over 100 in the proportion method. You're thinking of the rate method. So then on the other side, we have to match things up. We have the blank and we have the 90. Which one goes on top, the missing number or the 90? Well, it's of 90. You can think of that as out of 90. Implies the 90 is on bottom. 40 times 90 divided by 100 is 36. So 36 is 40% of 90. If you were doing that rate method, you would convert the percent to a rate, which is 0.4. 90 times 0.4 is 36. So you get the same answer. It's actually a little bit quicker that way. But we can run into problems like this. $42 is 60% of blank. If I'm doing my proportion method here, I start out with the 60%, which is 60 over 100. Where does the 42 go? On top. Very good. 42 is 60%, implying the 42 matches up with the 60. Cross multiply and divide, we get 70. So 42 is 60% of 70. If I wanted to use the rate method, 60% of course is 0.6. It would not be 42 times 0.6, it would be divided by. So that's one of the issues with the rate method, is you have to be able to look at the problem and decide, am I multiplying by that rate or dividing by that rate? If I am given the whole amount, then I'm multiplying by that rate. If I'm given the portion or the piece that I'm focusing in on, I would have to divide by it. Now that rate method does come useful because quite often we are given that whole amount and we are trying to find that piece out of it. For you guys, for example, for tolerances, if you have a resistor that is rated as 4.2 kilo ohms time or plus or minus 20%. You are given the whole amount, the 4.2 kilo ohms or 4,200 ohms is the full amount, and you can just multiply by the rate of 0.2, which is going to give you 840 ohms. That's your plus or minus. That's your tolerance. Actually, not your tolerance. I think it's called an allowance. The tolerance is actually 1680. So let's say you have a I'll make it easy on you. 3.5 kilo ohm resistor, plus or minus. What's gold stand for? 5%. Find the allowance like we did up here. What's the allowance going to be? $175 ohms? Okay. Another place where the rate method comes in handy, when you are wiring a house, sometimes it's code, sometimes it's just policy. But if you're coming into the house, if you're coming into the house right there, I need to go through the floor and up into a wall to a jack. And you measure out that distance. That this ends up being 28 feet, and then you're going to go up 2 feet to come out of the jack. So 30 feet total. But you have a required amount of slack that you need to leave in that wire for several reasons. One is for movement in the building. Hopefully there's not a lot of that. But second is for other mechanicals. If somebody needs to run ductwork and they need to be able to move that wire off to the side or anything else that's going to go into that house, they need to have the ability to move that wire slightly. So let's say that they're going to add 15% for slack. So how long does that wire need to be cut? Now, I'm not talking about what needs to be added to it, but how long does the total wire need to be cut? Well, the wire itself, 30 feet, that's 100%, right? That's the full length. But we need an additional 15%. So that wire has to come out to be a total of 115%. So yes, I know Ian's a step ahead of us there. So we take that 30 feet times the 1.15, and it does give us 34.5 feet. If you're looking at charts, So let's say the chart gives you distances and wire lengths required. And let's say it says if your distance is 20 feet, your wire length needs to be 1 of those days where things just, the hamster does not want to get on the wheel? Today. We'll just do that, 21.6 feet. 30 feet, it needs to be 32.4 feet. If your distance is 40 feet, it needs to be 43.2 feet. So what if you measure and your distance is 36 feet? How do we know how long to cut it? Well, there are a couple of ways we could go about doing this. I'm going to give you guys a minute to try this in your notes first, then we'll talk about it. So a couple ways we can go about this. One is we just go back to our proportions from before. We could say a 20-foot measured distance was 21.6 feet. So a 36 distance, cross multiply and divide is going to be what? 38.8 feet, yes. The other way you could have done it is you could have found the multiplier. You could have done 21.6 divided by 20, which is what, 1.08? And double check to make sure it's the same. 32.4 divided by 30 is also 1.08, which means you're adding what percent to the wire? If you're multiplying by 1.08, that means you have an extra 8%. Right? 1.08 is 108%. Right, Jordan? 1.08 is 108%. Okay. So that means you're just going to take the 36 times 1.08. 38.8. What do you think? You guys have one packet already. When you bought your textbook, did they give you that second little textbook with it?
Yeah, I didn't buy mine yet.
Okay. So in your little book, it's units 29 and 33. Then I'm going to give you another packet. It'll be page 255 through 256. 1 through 12.